Continuing on our talk about exponential functions, we're going to look at some of the ways that we apply these, especially when it comes to finance. But there are lots of other applications that involve exponential functions. Finance is just one that appears a lot. So let's go ahead and just define some terms that are going to come out as we talk about finances. One of them is interest. I think most of us understand that interest plays a role in a lot of things we do. It can work against us or for us, but it's basically a fee that's charged when we're borrowing some lender's money. So if somebody's lending money, usually we're going to pay interest by it, and we tend to use I for interest for that. The amount that you borrow, the original or initial amount borrowed, is called our principal, and we usually denote that with a capital P. The time period during which the borrower pays back the principal plus the interest is time, denoted by T. So usually that's going to be, sometimes it's years, but it can be other values. The interest rate is the percent that's charged for the use of the principal for our given period. The interest rate, denoted by R, is expressed as a decimal. Unless stated otherwise, the period is assumed to be 1 year. R is usually referred to in its annual rate, how much you pay over a year for that interest, even if you pay it back before then. And the amount of interest computed only on the principal is called simple interest. And so that's our first formula that we look at here. The simple interest on a principal P at a rate R, expressed as a decimal, per year for T years is this one here. Interest equals principal, the amount you borrowed, multiplied by rate, the amount you're being charged, which is a percentage of the principal, and then T would represent the amount of time that loan is outstanding. So simply looking at a simple interest calculation, Juanita's deposited $8,000 in a bank for 5 years at a simple interest rate of 6%. How much money will she receive? Okay, well, let's look at our formula there. I equal to PRT. Remember, I is the interest, the amount she's going to end up paying. My principal was the amount borrowed, so $8,000. The bank is borrowing $8,000 from her because she is putting it into the bank. The rate is at 6%, so we're going to put that as 0.06. And the time period during which this is borrowed is for 5 years, so we're going to multiply it by 5. Multiplying these out, we get 2,400. So over 5 years, she'll receive $2,400 in interest. So 2,400. The last question then is how much money will be in her account at the end of 5 years. If she doesn't touch it, it's going to be, so the total is going to be your principal plus the interest. So 8,000 plus 2,400, which gives us $10,400. And that's calculating with just simple interest, paying a fixed amount. We're always paying on the 8,000. So the 6% is calculated every year. In fact, if you just calculated it for 1 year, you'd see you get $480 every year. And then we're just multiplying it by 5 years, so we get that 2,400. Most loans, though, are not that simple. We rarely ever will actually calculate simple interest. Compound interest is really usually what we end up paying, and compound is the interest that we pay both on the principal and the accrued interest. So For example, on my previous, with this, when we looked at simple interest, it was $480 paid every year, basically. It's a fee, $480. But with compound interest, we every time we add money to that principal, we're also going to calculate my percentage based on that new total. So in compound interest, we end up paying a lot more interest because it's not just, the interest isn't just on the original principal, but it's also on the new totals that we get once we are paid that interest. So interest that is compounded annually is paid once a year, right? Annually, once a year. And then for interest compounded annually, the amount A in the account after T years would be given by this formula. So now we're actually getting into a formula that does involve exponents. So it's an exponential equation. What we have is our principal, and then we have 1 plus r. So whatever our rate of interest is, we're going to add 1 to it, and then we're going to raise it to the t power rather than just multiply by t. So let's take an example now. Let's go back to Juanita and her $8,000 deposit. How much money will she have in her account? So, here we go. So we're actually going to reverse it because the formula we have actually does tell us the amount she has in her account. A. So A is equal to the principal times 1 plus r raised to the t power. So my original principal was $8,000. Our rate of interest was 0.06, so that's 1 plus 0.06. And we're going to raise it to the t power, in this case, 5 years. So this is 8,000 times 1.06. Notice that that's a value above 1, right? So this is exponential growth, and we're raising it to the 5th power. Try that again. All right, plugging these into our calculators, we get $10,705.80 approximately. That's rounded. So she gets a little bit more in her account than what she had before. If you remember, what we had before was, let me go back. Yeah, it was $10,400. So with the annual compounding of that, every time that they paid her money, if that money stayed in the account, which it did, they paid interest. They paid 6% interest on that new total every year. And so that gave us about $305.80 more at the end of 5 years. Not a whole lot more, right? This is 5 years. It's $300 more, but hey, more is better. And the bigger that principal that we start out with, the more difference that extra amount of money can make. The second half asks, well, how much interest did she receive? So really, we just need to take our new total, the new amount that she has in her account, $10,705.80, and subtract out the $8,000 that she started out with. And we see that the difference there is $2,705.80. Now, this formula here was for compounding yearly. So once every year. In other words, you're paid the money once a year. Maybe it's at the very end of your calendar year there. You're paid that money. And then now you're earning interest on a slightly larger amount of money if that money is put into the account, which if it's just sitting in the account, it's compounding, right? It's being added to the previous. But let's make it a little more general because many times the interest isn't just paid once a year. It might be paid twice a year. We would call that semi-annual. It could be paid 4 times a year, which would be quarterly payments of interest. It may be paid every month, so monthly interest that's getting paid, or maybe every day you're getting paid a certain amount of money. So it's all about how many times a year it's compounded, how many years are paid. So this new formula here can reflect that, where the introduction here of N is the number of times interest is compounded each year, every time you're paid, and we've increased the amount now, after you've been paid, that is in the account, or that you owe if this is a debt, which is more like a credit card, right? So we're going to take the rate, we're going to divide it by the number of times you're going to get paid, and we're going to raise this to the number of years, but then we're going to multiply it by N, because N denotes how many times we're actually compounding it. And so it becomes part of the power as well. So let's take a look at what kind of a difference that can make. And I think it's a little more interesting, and they're using $100 here. I'm actually going to, let's change that. Let's make it a little more interesting. We'll make it $10,000. The larger the amount, the more you can see what a difference it can make. And we're going to have the same amount, right, put into a bank or what have you, and it's paying 5% annual interest, and find the future value A after 1 year. So we're just going to do 1 year and see what kind of a difference that would make with these different compounding things. So we'll start off with annual compounding. So again, I'm using 10,000 just to make it a little more interesting. R is going to be 5%, and T is only equal to 1. We're just going to do it for 1 year. And N, of course, is going to be the number of times interest is compounded, so it's paid out to you. When we're compounding it, we're paying it out, which increases the amount that you're earning. Since T is equal to 1, N times T is just going to be N. Okay, great. So let's just work these out. I'm going to start off with the formula. Plugging in what we know here, my 10,000 is my principal, my starting point. And for annual compounding, we're getting 5%. And that's divided by 1 because we're only compounding it once a year. And then we have 1 times 1, 1 year, and 1 time that it's compounded. This gives me 10,000 times 1.05 raised to the first power. And so we see for that first year, I get $10,500. So I was paid $500, 5% interest on 10,000. All right, not bad. Let's go for semi-annual. So semi means twice a year. So now we've got A equaling 10,000 multiplied by 1 plus 0.05, same rate, but we're splitting it up into 2 payments. So if you started in January, you get paid in the middle and then at the very end. And then that'll be 2 times my N times T for 1. So this gives me 10,000 times 1 plus 0.025 divided by 2 raised to the second power, which adding those together is just 1.025 and then squared. And this gives me $10,506.25. Cool. So I ended up making $6.25 more simply by compounding it twice within the year as opposed to only one time. Well, let's look at some other, what a difference it makes if I do it quarterly. So again, 10,000. And we're going to multiply that by 1 plus my 0.05. But now we're doing it quarterly, which means 4 times a year. And then that's 4 times the 1 year that I have. Putting that into my calculator all at once should get $10,509.45 approximately. All right, so doing it twice a year now, I made a few dollars more, about $3. It was instead of 106, it's 109, and that's simply by being paid out quarterly rather than twice a year. So I got paid twice more that year. What about monthly? All right, 10,000. Parentheses 1 plus 0.05 to the or divided by 12 now, raised to the 12 times 1. Putting this into my calculator, we see that we get $10,511.62. So again, it upped it by a couple more dollars as well, just by compounding it every month. Let's take a look and see if we did it on a daily basis that we were paid, and it was compounded daily. So this would give me 10,000, and we're still at 5% interest. But now we're going to compound it daily. There's 365 days a year. That's raised to the 365 for 1 year. What difference does this make? And we see that indeed it does still raise it. Now we're at $10,512.67. So going from monthly to daily made a difference of a little more than $1, which, what if we were talking about $100,000 here? That could mean a significant difference. This brings us to our a special number that we have, which it's the number E. Never thought you would hear that, probably. Now we're going to talk to you about the number E. But E is something that we use when we want to calculate interest continuously. It's a special irrational number. E repeats forever. When it's irrational, it repeats forever without a pattern. And that pattern that we see with E is 2.71, if we have E to the 1 power. 2.71828, and then it kind of continues on like that again without a pattern. So this is a formula we have for continuous compounding of interest. P is our principal still, R is the rate of interest, and T is time. So it definitely simplifies the formula we were working with before. As an example, find the amount when a principal of $8,300 is invested at 7.5% annual rate of interest, compounded continuously for 8 years and 3 months. All right, so our principal there is the amount of money, $8,300. Our 7.5% converts by moving the decimal back 2 places, 0.075. 8 years and 3 months. 3 months is a quarter of a year, so that would be 8.25 years. So plugging these in, we have 8,300 multiplied by E to the R, which is 0.075, multiplied by T, which is 8.25. So to the RT power. The E button on your calculator is something you want to look for. On some calculators, it's written above something, but usually you're going to look for E to the X. Mine is written above the LN button next to 4 on my TI 8384. And so I have to hit second to get to it. So I'm first going to type 8,300. Then I'm going to go times, and then I'm going to hit that E button. And I want to make sure I'm putting both of these in here, 0.075 times 8.25. You may need to put parentheses around that to show that, hey, this multiplication I'm doing is in the power. And what we see is this the amount in my account after that time period, 8 years and 3 months, would be $15,409.83 approximately. And that is with interest that is compounding continuously. What do you suppose that would have been had we done some other type of compounding, how would it compare? Let's say we did it for, let's just say we did a monthly payment there. And so we take our 8,300, we're going to go 1 plus 0.075, my rate of interest, and divide that by 12, and then raise it to the 12, and then that is for 8 years. So, calculating this out, we see that this would come out to $15,095.37, which, oops, I think I did something incorrect. I'm not supposed to multiply by 8. I had an 8, but it should be 8.25. So let me fix that. 8.25. And then I need to fix my calculation. And we'll see what a difference that makes. Okay, so it actually would come out then to $15,380.18. Still, about a $30 difference there between the two, which isn't much, but the only difference there is how often we're compounding, continuously versus monthly. And little changes like that can make big differences over longer periods of time. And when our interest rate is different and our principals are different, those numbers can make big differences. So let's look at the properties of this e thing. F of x to e to the x. This is e is, as we saw, that 2.7 value. You can see then that what we have is an exponential growth with this. And here we have some contrasting ones. Notice they're all going through 1, right? 0, 1. Anything to the 0 power is 1. This is y equal to 2 to the x. And then we have y, the green is y equal 3 to the x. You can see that e is kind of right in between those two numbers, e to the x. Remembering the base of e is 2.7, et cetera, et cetera, et cetera. And so it doesn't rise quite as fast as 3 with the base, but it rises much faster than with a base of 2. So, yeah, that's what we call this the natural exponential function. This is what we see a lot of times with natural growth of populations and different types of just natural phenomena where the exponential growth of something takes on just kind of a natural thing. Think about mold growing in a petri dish or something to that effect. That's continual adding, continual compounding of things. And so we see this e taking place naturally, and that's why we call it the natural exponential function. This works also with decay. So we have natural growth and then we have natural decay. But with the e, you can see both. With k greater than 0, k being up here, we have exponential growth. And a would be our starting, kind of our principal, whatever we're starting at. That can also represent a population, an amount of a radioactive substance. Then we have, and the sub-zero there is simply meaning the starting point. So we're starting with this point where time is equal to 0. We're going to take that, multiply it by e to the kt. And what is k? K is the relative rate of our growth. So that's our rate of growth. With the money, it was the interest. Or decay. If k is more than 0 or k is less than 0, it's a decay. And here we have negative k there. So when k is a negative number, in other words, we see decay. When k is a positive value, we see growth. And t, of course, is time. All right, so in the year 2000, we're going to look at the natural growth here. The human population of the world was approximately 6 billion. That was 21 years ago. And the annual rate of growth was about 2.1%. Using the model in the previous slide, estimate the population of the world in the following years. So let's start off with 2030, which is 9 years away from where we are right now. We're going to use 2000 as kind of my starting point. So the year 2000, year 2000, this is going to be my time equal to 0. This is going to be my starting point. And the formula here, A, would be my amount. Okay, we're talking about people, but we're starting off with 6 billion. So we're just going to use 6. I'm not going to use all those zeros. We're just going to assume our numbers are in billions. We're going to multiply that by E times R, the rate of growth, or K was our rate of growth. So that's 0.021, 0.021. And then for the year 2030, if the starting point was the year 2000, this would be multiplied by 30. And we can see this. So T equal to 30 would be the year 2030. Putting this into our calculators, we see it's almost double over those 10 years, 11.265, and this would be in billions of people. So over that period of 30 years, right, starting from 2000, we saw an almost doubling of the world's population over a course of 30 years. Sorry. All right, what about 1990? What would that be in terms of the year 2000? If the year 2000 is 0, then that would be a time difference of 10 years previously, so negative 10. We can even see that here. 0.021, negative 10. What would that take us back to in the year 1990? Putting it into our calculator. So 10 years previous, we see 4.863 billion people when I have the negative 10 there. So these are some just examples of the power of exponential growth. We can see that just shaving off 10 years took us about 1.2 billion fewer people in the world. And then 30 years ahead, we saw only over 30 years, it almost double from 6 to almost 12 billion people. Exponential growth, as we can see from the graphs, get really big, really fast. There comes a point where we have slow growth, and then it just like takes off, right? And it continues to get steeper and steeper and steeper as it grows. In fact, exponential growth was Albert Einstein called it one of the wonders of the world. Because it is a fascinating thing to see how something can grow super, super fast. One of the things that I like to, which most of you hopefully can relate to, is bread that I find in my refrigerator, or not on but in my shelves. I usually don't refrigerate my bread. But you may notice like one day, oh, there's a piece of mold on this piece of bread, but then you maybe neglect to throw it away. And then within like 1 or 2 days, the entire thing can just be covered in mold if you don't throw it away, which unfortunately sometimes I haven't. So you start off with just a couple of spores here and there, but those spores give us more spores, and you have that continuous growth from that mold, and all of a sudden the whole thing just explodes, and that's what we call exponential growth.